I'm staring at the camera here, but this is a repeat of some of the points I have already made in the earlier podcast, but to keep this module as independent as possible, I'm going to try to repeat some of the points. We are using the main paper I'm using here for this series on evolution of carbon cycle and climate regulation is this one. Which has a nice simplified cartoon illustrating the inorganic portion of the long-term carbon cycle. Long-term is important here because we are going to mostly focus on the evolution over geologic timescales. So we already mentioned metamorphic and volcanic degassing of CO2. We have terrestrial weathering, which brings in the alkalinity related CO2 sinks into the water bodies, oceans, lakes, rivers, and so on. And there is sequestration of calcium carbonate and organic carbon, which typically we represent as CH2O. When you do photosynthesis, you do C6H12O6 and so on. The ocean processes include marine weathering, where CO2 is taken up to produce bicarbonate, and there is a reverse weathering, as we will see, where the bicarbonate is converted back to CO2. So all these processes matter on longer time scales, as we mentioned in the previous podcasts. Silicate carbonate weathering cycles and how much happens on land versus how much happens in the ocean and so on are still estimates, but one can look at the estimates of modern Earth surface carbon reservoirs as well. I'll show a couple of ways in which we look at this. So this is in 10 to the 18 moles. I'm sure you are introduced to the concept of mole by now. So ocean has 2.8, atmosphere is tiny in terms of the reservoir size. Soil is much smaller than the ocean, as you can expect, 0.3. Terrestrial biosphere doesn't have much of carbon storage either, 0.06, but whatever there is very important in terms of the forest biomass and the global warming, uptake of the anthropogenic CO2, and this constant debate about whether trees are solution or not, and what happens when wildfires come and destroy forests and release all that carbon suddenly, etc., etc., etc. Marine biosphere has 0.05, again similar to the terrestrial biosphere. The upper continental crust has 6,250, the largest one here. Carbonate carbon in rocks is estimated at 5,000, and organic carbon in rocks is estimated at 1,250. But we already talked about the potential uncertainties in these estimates, especially in terms of whether this carbonate comes from silicate rock weathering or it is returned from silicate rock weathering, or whether biology adds a lot, and so on and so forth. We keep looking for evidences of carbon variations through Earth's history, of course. The nice long record from the Vostok ice cores in Antarctica and shorter ones from Greenland and elsewhere keep adding to our knowledge. This one was originally about 400,000 years. Now it's been extended back to 800,000 years, where we have glacial, deglacial cycles. You see the asymmetry here, which is discussed elsewhere in terms of the rapid changes during a deglacial stage, which is what technically we are in because we are warming and melting glaciers. It takes much longer to build glaciers than to melt them because of the ice albedo feedbacks, temperature changes, atmosphere getting drier, snowfall rates getting slower and slower. And there is the big question of exactly what determines this 80 to 100 ppm change from glacial to deglacial and back. There are many hypotheses, which means that we don't know for sure whether there is only one mechanism working or there are multiple mechanisms working. All our interest is now obviously because of what's happening since Industrial Revolution. If we zoom in, First of all, you see that we have shot past anything we have seen in the last 800,000 in this years in this record, or there are many more coarser resolution records which show that we are growing at the fastest rate in a many million years. So since the last millennium and since the Industrial Revolution, we have started burning fossil fuel, started with coal, now oil, gas, coal, and lots of other land use contributing as well. We are increasing CO2, and it's increasing at about 4 ppm per year in the atmospheric reservoir. So atmosphere at the time this was drawn was at 800, but now it's at 840 or so, I think. And we not only look at reservoirs, which we already did, like here in gigatons carbon, flux would be gigaton carbon per year, and the reservoir is the size estimated in gigatons. So soil, fossil fuel pool, which we are extracting and burning and putting it into various reservoirs. There is reactive sediments. Deep ocean is a big reservoir. We saw continental crust is a massive reservoir. We will see in a minute that the in general, rocks and crust store lots of carbon, but we are also always interested in the fluxes, where the CO2 is going, where it's coming out, the sources and sinks, other than the fossil fuel source, which is here at 9 gigaton of carbon per year. So that includes fossil fuels, cement production, which is very polluting, land use change like deforestation, agriculture, urbanization, etc. When you do flux in carbon or CO2, there is a conversion factor of 3.7, which you have to be careful about. So people keep switching between carbon and carbon dioxide, or even carbon dioxide equivalent, because you have to convert methane, N2O, CFCs, and other greenhouse gases into carbon equivalents when you want to look at certain things like impacts on radiation balance, etc. So only thing to note is that when you look at the fluxes, you have photosynthesis taking up about 120 plus minus 3 gigaton carbon, out of which plant respiration puts back 60 gigatons, and microbial respiration and decomposition puts back 60 gigatons, and plant biomass hold about 550 as a reservoir. So these are fluxes per year. So this is a big challenge, that the uptake or sink and source often tend to be very close to each other. So it's these tiny differences and how they are changing because of the warming and precipitation changes, sea level rise, everything else. Because of this fossil fuel, this anthropogenic emission is causing climate change, which tends to perturb all these fluxes. For example, the ocean is taking up somewhere between 90 plus 2, so this number plus 3 is the additional amount being taken up because of the increasing carbon dioxide from anthropogenic emissions. So it puts out about 90, so you can see that there are tiny differences between large numbers. Sorry, I said that's uncertainty, but that's actually additional sink. And the net uptake in the ocean is 2 gigaton carbon per year, but you can see that that's a difference between two large numbers. Surface ocean has a reservoir of about 1000 gigatons, but deep ocean has 37,000 gigatons, which is very critical. Okay, so in terms of emissions, here are the carbon dioxide emissions by source since 1880, sorry, and obviously we are increasing. Land use changes here, coal burning, supposed to be phased out, is happening, but we are still using a lot. Oil, gas, and other. And where is it all going? So if you look at the annual emissions in this gray line here, which is the line shown here in terms of gigaton carbon per year. Again, gigaton CO2 and gigaton carbon, but get used to it. Ocean sink is growing. Question is whether it's saturating. Land sink is growing. Again, question is what's happening to it, whether it will remain the same size, whether it will increase or it will decrease. And the remaining, of course, grows in the atmosphere, and there are some imbalances, as we will see in a minute, or residual residuals which are not closed in terms of the estimates. Here is another way to look at it: anthropogenic carbon flows. So this is again in CO2 equivalent now. So this is gigaton carbon here, showing fossil fuel CO2, what we just saw, coal, oil and gas. That's how much it's increasing. This is land use change adding to that, and this is the land uptake, which subtracts, the ocean uptake, which subtracts, and what accumulates in the atmosphere. And here we see the budget imbalance better. So it's good to see it in many ways, so you get a sense of how the accounting happens. So these are the reservoir changes, and these are the mean fluxes in gigaton carbon per year now. These numbers are what we were using here. So this is another way to see 9.5 gigaton carbon per year from fossil fuel burning, land use and other things included. This is of course land use change adding the flux of 1.5 gigaton carbon per year. Land uptake is at 3.2 gigaton carbon per year with these uncertainties or standard deviations shown there. This is the ocean uptake, this is the accumulation in the atmosphere, and that's the imbalance in terms of fluxes. Okay, this is another way to see, just because this gives you a sense of the relative size of the reservoirs. So again, just keep looking at these numbers. It's good to repeat them so that you get at least the approximate order of magnitude of each reservoir. Soils and vegetation is much larger than what's in the permafrost. Permafrosts are thawing, and there is always the worry that they will add to the acceleration of global warming. So that's much smaller, or slightly smaller than soil and vegetation. But polar amplification and warming patterns being faster at higher latitudes are obviously a concern. There is the atmospheric number that's much closer to the present. Industrial emissions, the bullet size here. Land use, land change, 185 gigaton carbon. This is continental crusts and upper mantle, basically stored up and not easily released. And surface ocean is much smaller than the deep and intermediate ocean, which is at 37,100 gigatons of carbon. Okay, where is it stored as organic carbon? Obviously, ocean has a lot of organic carbon, and it moves into different pools. This is all the inorganic and organic carbon pools are relatively small, but just to get a sense, organic carbon in gigaton carbon per year, above and below ground phytomass, so topsoil and subsoil. I won't go to the detail, but tropical wet, tropical moist, and tropical dry forests. So you have to see the relative sizes depends on the net balance of respiration by microbes and so on, as well as so just because this is tropical wet doesn't mean it's higher than tropical moist. So the net balance is what matters. Oops. And tropical dry is almost similar to tropical wet in terms of topsoil and subsoil, for example. Tropical montane ecosystems, warm temperate moist, warm temperate dry, cooler temperate moist. Respiration rates get smaller and smaller as temperatures go down. With global warming, this is something we have to worry about. Cool temperate dry, much smaller than moist. Boreal moist, topsoil and subsoil, fairly the largest of the reservoirs of organic carbon reservoirs in over land, and there is boreal dry. Okay, just keep in mind the relative sizes of these reservoirs plus the kind of dependence on the ecosystems and latitudes, and especially temperatures, which control heterotrophic respiration and release of carbon. This is the nice figure from Friedlingstein, Pierre et al. From 2020, which is the estimate for 2009, 2010 to 2019 average gigaton carbon per year, showing again what we've been looking at: volcanic input, fossil fuel, fossil CO2 output, what is in store for in terms of gas reserves, oil reserves, coal reserves, what's in permafrost, what's in soils. Now this shows a larger range. Before we said 2300 gigatons, but you can see there is a range there. Those are the fluxes we talked about. So almost balanced, but land is taking up 1.5 gigaton per year or so. That's what land use is releasing. This is what land uptake is. Okay, what's stored in vegetation in gigatons of carbon, what is happening with reservoirs and lakes in terms of recycling, what's happening in the coasts, subsurface sediments, organic carbon here now separated in the ocean, and the biological and solubility pump, which we have talked about before, what's in the marine biota, so biomass in itself, relative size of the dissolved inorganic carbon in the ocean at 3800 gigaton carbon, and the atmosphere here now as of 2019 was accumulating at plus 5.1 gigaton carbon, stands at 860 gigaton carbon. So you can see that the numbers change even in these figures depending on when they were made. This says 839, the previous one said increasing at 4 gigaton carbon per year. This one is at 5.1, and the reservoir size here is 860. Ocean is taking up at 2.5 with a range of 1.9 to 3.1, which gives you a better sense of the uncertainty. Okay, so a quick look, but you can make sure you look at it again carefully and understand the fluxes, sources, sinks, and reservoirs. And we obviously have to now go back and start worrying about the processes on long time scales. We're not going to worry about short anthropogenic time scales, except we'll touch on it at the end in terms of the future of carbon. Okay, so the goal here is to look at processes like weathering, reverse weathering, and other reactions like metamorphosis to understand evolution of carbon cycle on Earth history time scale and how it regulated climate over the same time scale. Okay.